In this session, uh, we are going to slightly deviate from the original constraint that we had adopted while studying thermodynamics. We were looking at the thermodynamics of phase rule, and we said the strength of that particular treatment is you don't need to know what is the nature of the molecules to which you are applying it. So that also becomes the limitation, because then when you want to bring to the table your tacit knowledge and understanding of physical systems, you need to know the relationship between the molecular structure and molecular properties with some of the parameters in thermodynamics. So we are going to have a look at that aspect of thermodynamics, which is with the help of the Hansen solubility parameters, and also introduce what is called the group contribution methods. Have you studied group contribution methods so far? Not yet? Unifact method you have studied?
Yes,
that itself is a group contribution method. Okay, so you know the contributions of small functional groups to certain properties of that the contribution they can make to a larger molecule comprising several parts of those small components. So that's a group contribution method, but it's a very important approach, and we need to have some physical feel for using that particular approach. So we'll do that today, the Hansen solubility parameters as well as the group contribution method. In the last session, I got an impression that although we did the sum in terms of its mathematics, the physical significance of the lowest operational use temperature was something which was not very clear, and we did not have much time to really discuss that aspect. So therefore I thought that let us clarify that issue first before we go towards the group contribution method and Hansen solubility parameter. So the anti-icing liquid, as it is sprayed on this aeroplane, its objective is to form a layer on the surface of the aeroplane, so that when a snowfall is there, that snow can get mixed with the anti-icing liquid and it can liquidate the ice layer or the snow layer, and therefore the plane can take off. Generally, for a Boeing aircraft carrying say about 300 passengers, the speed which is required is about 350 kilometers before it can take off. Now, if you have snow here, the aerofoil characteristics are so changed that the plane does not acquire that kind of a lift at the speed of 350 kilometers per hour. So there is a regulation in all airports that the aeroplane must satisfy a certain holdover time. So once it is cleaned off all the snow which has fallen on the wings, and you deposit the anti-icing liquid on the surface of the wings, then before the effectiveness of the anti-icing liquid is completely exhausted, the plane has to take off, and that time available for the aeroplane is called the holdover time. Now, the mixture which is formed between the ice and the anti-icing liquid has to be at a very low viscosity. Okay, but we cannot really supply the anti-icing liquid, as it is called, at a very low concentration, because then the packaging cost becomes very high, and therefore usually the anti-icing products are concentrated. Here the problem which I had given, the concentration was 90% mole weight fraction of the ethylene glycol, and the recommendation was that you mix about 50-50 of water with this, so that you get an anti-icing liquid which is about 0.45 mole weight fraction of ethylene glycol. Remaining is water. So if this is the kind of a operating liquid, now this operating liquid is effective only up to a certain ambient temperature. Okay. Now what is that ambient temperature? That is the lowest operational use temperature as has been defined. And if at this concentration we simply draw a line downwards like this, which is about say 45% of ethylene glycol, wherever it meets the liquidus line, you get the lowest operating use temperature. We had a doubt, why not go below this temperature also, because you are still going to have the liquid here and it may be effective. So we are going to carry out a very small thought experiment to find out how this material is going to be effective at different ambient operating temperatures. So for which we will first require the liquidus line of the molten liquid in equilibrium with ice or snow, and we have already derived this kind of an expression which tells us that the mole fraction of the component A in the liquid phase in equilibrium with pure solid, which is ice, is going to be exponential of minus alpha A. Alpha A is a function of the gap between the solid and the liquid phase for pure A, and the final expression that we had derived was this one, which is an approximate expression. So it is valid for temperatures which are closer to the melting point. Fine. Now for the ice, the melting point is 0 degree centigrade, 273.15 degree Kelvin. Latent heat of melting of ice is 80 calories, multiply that by 4.18 and you will get in the joules per kg. So we will, this is the kind of a liquidus line that you get with the help of the procedure that we have already derived. So this is the liquidus line which I have calculated and plotted here, and with this liquidus line, if this anti-icing liquid, I drop this right through, I get an L out which is minus 20.55 degrees centigrade. Okay. So let us see how this anti-icing liquid is going to be effective at different ambient temperatures. The case 1, for the sake of simplicity, let us assume that the snow per meter square of the area is only 1 kilogram and the anti-icing liquid is also 1 kilogram per meter square of the surface of the plane. So therefore, if 1 kilogram of this composition with 1 kilogram of this composition, which is the pure ice, we will get approximately which is 0.225 as the weight fraction of the ethylene glycol. Okay. So you have ice here at 0 degree centigrade, you have anti-icing liquid here at the same temperature, at the ambient temperature, and when you mix the two together, you will come to this particular point. Now this point you realize is in this region which is the molten liquid region. So therefore that entire 1 kilogram of ice would be completely molten into the dilute solution of ethylene glycol, and it will drip off the aeroplane surface, and therefore the anti-icing liquid is very effective at this temperature, which is 0 degree centigrade. Now let us look at another temperature which is minus 8.5 degree centigrade. Okay. Now the mixture of ice and mixture or the snow and this anti-icing liquid will have this overall composition, which is same, shown by the star here. Okay. Now if you just drop this line here, you can see this is equidistant from the ice and from the liquidus line. What it means is that 1 kilogram of this anti-icing liquid which was mixed with 1 kilogram of solid snow, when you drop it here, only the temperature drops, but the 1 kilogram of snow is still there. This is the liquidus light. So when you are here at this particular point, fine. So minus 8.5 is this particular point, fine. So at this point, when you drop this line, 1 kilogram of ice mixed with 1 kilogram of the anti-icing liquid brings the ice to this particular point. What it means is that the 1 kilogram of ice or snow is completely molten in presence of 1 kilogram of anti-icing liquid at minus 8.5 degrees centigrade. Okay, is this clear now? So the capacity to melt the ice is completely exhausted at minus 8.5 if the equal quantities of snow and equal quantities of the anti-icing liquid are mixed together. So this is the case too. At minus 8.5, the plane is safe because you are able to liquidate the entire quantity of snow which is present on the surface. But that is the limiting capacity of the anti-icing liquid. The next is you go to this L out case. Okay. Now in case of L out, now when you have 1 kilogram of anti-icing liquid which is mixed with 1 kilogram of ice, you can see that it is equidistant. This is same as this distance, right? If you apply the lever rule or simply carry out a material balance, you would realize that the 1 kilogram of ice will remain as such in the solid form and the 1 kilogram of anti-icing liquid will remain as a liquid. So therefore on the surface of the aeroplane you will have a 2 kilogram mass with 1 kilogram of ice and 1 kilogram of anti-icing liquid. So therefore this anti-icing liquid is not performing and delivering the function that we want it to perform now at this particular temperature. So it has not really molten any single gram of snow. Now let us take the case 4. Now in this particular case, we are considering a temperature which is minus 33 degrees centigrade. Okay. So this is the tie line for the minus 33 degrees centigrade. The mass composition of the ice 1 kilogram and anti-icing liquid 1 kilogram is again the same. But now this mixture is split between ice and a liquid solution, molten liquid, which is of this composition, and that happens to be 0.6, which is given here mass fraction. Okay. Now can somebody quickly calculate? This is total mass is 2 kilogram. There are two masses here. There is ice there without any ethylene glycol, and there is this molten liquid which contains the entire quantity of ethylene glycol which was there in this original anti-icing liquid. So how much of ice would be there and how much of anti-icing liquid would be there? Can you just calculate? It's a simple mass balance for ethylene glycol and then for water. So कितना आ रहा है? See, if this point happens to be very close to this, it will be entirely ice. So the quantity of ice is not proportional to this distance but inversely proportional to this. It's a lever rule. So that is why I am asking you to do it, because only then you would realize all these things. So you do the material balance, you would immediately realize it. Yes. So the result is that you will have 1.25 kilograms of ice, okay, and 0.75 kilograms of aqueous ethylene glycol. What it means is the anti-icing liquid in fact froze and therefore it deposited some ice onto the plane. So that is the physical significance of the L out. So below that temperature, the anti-icing liquid will be in fact detrimental for the flight of the aeroplane. Fine. So this was the significance. I just wanted to go through this so that you start thinking about such physical significances of the calculations that you do. Okay. So next part is Hansen solubility parameters and the group contribution method. Okay. See, in all along we have said that we know more than what we can actually state and what we know, as we know. So there is a lot of tacit knowledge and there is a lot of a priori knowledge with us from our primary exposure to nature around us, as well as what we have studied and interpreted internally without articulating it in our own words. And we make use of such kind of a knowledge to guess what is likely to be an answer, which is a kind of a hypothesis. So in the case of hexane and water, we guess this is likely to be the hypothetical phase diagram for this totally immiscible pair of liquids. And knowing this fact, then we started looking at how these liquidous lines can be estimated. Now the question is that what is the source of this intuition or the tacit knowledge? Fine. So it is not all that intuitive. It also depends upon what else you know about the system. And this, the more we know about the system from very different dimensions and different fields of activities, fields of consideration, you can bring that knowledge here. And so just to go towards these concepts, first let us attempt to explain the following two different behaviors. Okay, this is an ideal vapor liquid behavior between say methanol and water. It is not as ideal as say toluene and say benzene. Fine. But it is still extremely ideal. And then we have hexane and water, where you have this particular line is completely liquid hexane phase. This line is the completely water phase, nearly pure water with thermodynamic activity almost equal to 1, mole fraction equal to 1. Nearly pure hexane, thermodynamic activity equal to 1, mole fraction equal to 1. Okay. So this is the difference between these two. And if we look at the variation in the thermodynamic activities, we can say that the activity of methanol in this particular mixture is going to be equal to its mole fraction. Fine. Activity water is going to be equal to mole fraction, and the activity coefficients of both are going to be equal to 1. Fine. But what happens on this axis and this axis? The mole fraction, activity, mole fraction of water, activity of water, etc. So this is something that we need to now write down and then understand how they have undergone a change. Okay. So as far as say hexane is concerned, the mole fraction of hexane going from here up to here, it started with nearly pure hexane liquid. So therefore I have given approximately equal to 1, and at this boiling point it became equal to 1. And activity of hexane was equal to 1 all the time. Here it was nearly 1, but then it became exactly 1. Similarly for water, we have a similar situation on this side. But on the hexane liquid phase, the mole fraction of water was always nearly 0. Initially it was nearly 0 and then it became perfectly 0 at the boiling point. And the activity of water was nearly 1 while it was here, but the activity of water became equal to 0 at the boiling point of hexane. Fine. And here similar way we have. Now what happens to the activity coefficient? The activity coefficient of hexane is nearly 1 all the time from here to here. Activity coefficient of water is infinity here because concentration is 0 multiplied by this infinity brings the product equal to 1. Fine. So the activity of water here in the liquid phase was almost infinity, and then it became equal to, it will become 0 here once all the water is lost. And similarly here. The question is, how do you get these activity coefficients? They are not available from thermodynamic considerations, but then we have to go for the molecular considerations. But before that, let us understand the origin of these activity coefficients within the thermodynamic framework. Supposing you have a liquid and it is XA moles, another liquid B, XB moles, but the XA and XB are such that the total of the two is equal to 1 mole. Fine. And supposing we just pour one of these on top of the other, and because of their density differences they are not mixed at all, so the total mass is 1, and then what is the Gibbs free energy for this total of 1 mole mass? It is going to be equal to XA into the molar Gibbs free energy of A in the liquid state plus XB multiplied by the molar Gibbs free energy of the component B in the liquid state. So this is state before mixing. They are just poured one above the other. Fine. Now this, therefore, G total can be expressed like this: GLA plus XB multiplied by GLB minus GLA, which is really this straight line. So if you vary the XA and XB, you will get this particular line, which is a straight line. So the total molar, total Gibbs free energy of this particular system for 1 mole is a straight line like this. The question is, will the system phase separate upon intimate mixing? Fine. The answer will depend on the nature of G total after mixing. Here they are not mixed together, just they are layered one above the other. Fine. Now the after mixing, the G total is going to be, which is the G solution, the mole fraction of A multiplied by chemical potential of A plus mole fraction of B multiplied by chemical potential of B. So physical chemistry Atkins will actually show you this. It is also apparent, we can simply say it like this, that chemical potential of A is nothing but partial molar Gibbs free energy of the system when the A is changed, okay, keeping the other composition constant. Fine. So therefore, from that definition itself you can derive this expression. Fine. So as long as the composition remains the same, XA and XB, fine, the G solution is like this. Now this is the total and this is after mixing.
We don't invoke whether they are phase separate.
No, at this, no. So for an now we are going to look at that. Okay. Now for an ideal pair of components, G of solution is going to be XA multiplied by certain things here and XB multiplied by this, and we know this, what is the expression for this value, because G of solution is XA into, we have done this earlier. No, RT ln X. Okay. So mu of this particular value, chemical potential, is defined like this by Gilbert-Lewis. Okay, so GLA plus RT ln x, XB multiplied by GLB plus RT ln XB. So now we invoke what the definition of the chemical potential by Gilbert-Lewis, and if we rearrange this, so put XA equal to 1 minus XB, rearrange all this, what you will get is GLA plus XB multiplied by GLB minus, this is nothing but that particular straight line before mixing, and this is the remaining component of that. Okay. So what will be the shape of this particular curve? The shape of this particular curve will be then estimated. So this particular line happens to be a simple linear expression for keeping one layer above the other layer. Okay. Now this particular part of the expression, can somebody estimate what is the value of this at, say, for example, XA equal to 0.5, XB equal to 0.5? Quickly calculate. XA equal to 0.5, XB equal to 0.5. Don't calculate RT, just this one. The expression in the bracket. And it has a negative sign. Okay. So therefore, at 0.5 value here, this point is fixed, multiplied by RT. Okay. But as XA goes to 0 and XB goes to 0, we have a problem. Because you cannot estimate this. Do you realize that? Huh? We have to now invoke L'Hospital's rule, and if we invoke that, we can then find out that the values go to 0, and therefore that particular curve touches here. So this is the for an ideal solution where when you mix two components, their affinity towards each other and affinity towards the other component is identical. When they mix together, there is no volume change with respect to the volume at unmixed state. Okay, it's an ideal solution. You get this kind of a curve. You can see what are the components of this curve. This is that linear part here, and this is the molecular contribution due to mixing. So this is at molecular level, mixing has taken place, and this is this particular contribution. Okay, and this is the G of solution. Fine. This is the G total before mixing. This is the G of solution after mixing, and this is the contribution of the molecular contribution because of mixing for an ideal component mixture. Fine. Now this value, you would realize, is also, this term is first of all always negative, and it is also the entropy of the system, because if you take the total Gibbs free energy, take a partial derivative with respect to T, okay, the first term vanishes. In the second term, what you get is only this much. So this is nothing but the S in the definition of Gibbs free energy. So this is the entropy, okay, and it's a measure of entropy of mixing, whether the solution is ideal or non-ideal if molecules are perfectly randomly distributed in the solution. Fine. So this contribution is considered to be entropic, and this mixture will not separate into two liquid phases, because if you mix A and B at any particular value of A or B, the mixed system will have Gibbs free energy which is lower than this particular state, which is unmixed A and B, right? So this is the reason why ideal liquids, when you mix them together, because of the entropic contribution, they will actually show a non-separation of two phases. Fine. So when do you start getting the separation of phases? You start getting the separation of phases when the system is comprising of non-ideal pairs, and therefore the particular expression in the bracket, which is the chemical potential of A, cannot be expressed simply as GLA plus RT ln XA, but we have to introduce now the activity of A, okay, which is the contribution of Gilbert, Lewis. Fine. So we rearrange it again and we get this expression. So this is the contribution of molecular mixing. Fine. It will have again two components, which is the entropic as well as the enthalpic contribution now. In the previous case, there is no enthalpic contribution, because when you take these definitions of G and then you find that that particular expression which we had got was only a contribution of entropy, because that was the partial derivative of G with respect to T. So now you have this expression, which is the entropic contribution, and this expression, which is the enthalpic contribution. If total volume of mixture remains unchanged during the mixing, and this entire derivation is at constant temperature and pressure. Fine. So here there is no work done on the external system, so that component is not introduced into this because there is no volume change. The activity coefficients are related to enthalpy of mixing. This is the conclusion that we are drawing from this. And the enthalpy of mixing, because the activity coefficients depend upon enthalpy of mixing, what happens is the mixture may separate into two liquid phases if enthalpy of mixing and hence activity coefficient distort the G curve, which we had seen earlier for the ideal case. So what happens? Because of the enthalpic contribution, when activity coefficients are extremely high, you start getting such kind of distortions. So this was the original unmixed state. This was the state for the ideal mixture of A and B, and this is the enthalpic contribution because of which it has gone like this. Now look at the situation. Supposing you have a system which is say XB equal to say 0.8 here. Fine. So this will be a uniform solution. Fine. Because this is the lowest state that you can get here. There is nothing else. You reduce the XB, come here, and again you will have the same XB. Fine. Now you reduce the value of XB and come here, and then suddenly you realize that going to this, your Gibbs free energy is going to increase. Instead of that, the system spontaneously decides to split between 2 points, this point and this point. So when the XB value is here, you get two liquids, one with a concentration given here, another with a concentration given here, and they will be split according to the lever rule depending upon the value of XB, and the two-phase mixture of the two will give you a lower Gibbs free energy than a uniform solution of the two components. That is why they split. Okay? And when you further decrease XB, you again start getting the uniform solution. So this is why, so all your phase, heterogeneous phase equilibria would reflect some kind of distortion in the Gibbs free energy of the system as shown here. When you go into finer details, you will find more nuances in this. Okay. For example, here I came from here to here. Okay. And it was uniform solution. Fine. But then what happens is, as soon as I come here, it splits. Fine. But look at this portion. So if you start from xa equal to 1, you come up to here, the lowest point here, you are a uniform solution. Not only that, you can go to slightly higher concentration and you are still uniform. Only when you enter the region between these two lines, okay, they split up. So the region here is actually the cause of the spinodal decomposition. It is not the subject of study for us today, but when we go into more details of how phase separation takes place and how micromechanical structures can be manipulated, you need to understand the spinodal decomposition which takes place. Okay. So the next question is, how do we know more about enthalpy of mixing and hence activity coefficients? Now we have to go to molecular considerations. Thermodynamics has that limit, fine, which is the thermodynamics of Gibbs. So when we need to use molecular information, there are several approaches to this problem, okay? But one pragmatic approach, and which is very useful for creative thinking, is the Hildebrand solubility parameter, because it does not require large amount of computation, etc., and lot of data is already available. Fine. So it's a very simplistic approach, but when you want to really quickly arrive at a hypothesis, it does help you to postulate a hypothesis. These are related to cohesive energy densities of A and B, okay, which in turn are related to the enthalpy of vaporization per unit volume. So delta A and delta B are high when the cohesive energies are large. Fine. So for example, for water they will be very high because the latent heat of vaporization is high. So we don't go into the rigorous derivation of these parameters, but then let us look at its manifestation, the origin of this, okay. So which are the molecular parameters which contribute to this enthalpy of mixing? Now there are several, but three are identified by Hansen as the most important. One is the dispersive contribution. Now what is dispersive contribution? You have said two molecules, each one has its own electron cloud, and for some reason, because of thermal fluctuations, if the electron cloud undergoes a kind of a fluctuation here. Now once this undergoes a fluctuation here, there is a dipole which is instantaneously created here. Now once this dipole is created, it induces a dipole on the neighborhood. So the motivation may be one molecule because of its thermal fluctuation, but that results into the induced dipole being formed on the molecules in the neighborhood. Now they start attracting each other. Fine. So this, for example, attraction, if I consider two molecules, say one something like about hydrogen and second say something like carbon tetrachloride, which one will have more dispersive attractive interaction? Yeah, so you can see the dispersive interaction is highest for those molecules which exhibit very high electron density. Okay, and such molecules also exhibit very high refractive index, because refractive index is again dependent on the electron density. So molecules having very high refractive index would have very high. So but I am giving you these clues because you may know something, about the refractive index from experiments from physics. But when you are solving a problem in chemical engineering, suddenly that information becomes useful to you. A molecule which has got a very high refractive index would also have very high dispersive interaction. Fine. The second interaction is the hydrogen bonding interaction, which is because of the polarization of a permanent dipole which is there between water and the protons in this particular structure, and then two water molecules will tend to align themselves in this particular manner, in such a manner that this will be a hydrogen bond which will be formed. Okay, it is not as strong as this hydrogen and this oxygen, which is a covalent bond. Fine, but this hydrogen bond is reasonably strong as compared to the dispersive interactions molecules may have. So it is stronger than the dispersive interactions. Fine. Now, as a result, what happens is water generally, okay, because of these interactions, will form almost a fimer. So usually 5 molecules on an average come together and they form this kind of small short chains, and therefore you would be surprised when you start looking at the conductivity of or rather the contribution to conductivity because of protons. For water it is quite high because it is like a pulse which goes from one end of the chain to another end of the chain, as compared to hydroxyl ions. Fine. So these are the kind of clusters which are formed, and there are a lot of theories about it. One is Verdheim theory, there is Pancho's theory. So there are so many different theories to actually estimate the hydrogen bonding behavior of water. But this is a fairly strong interaction, and which must bear in mind, which is here in this particular case is between two water molecules, but in abstract terms it is a electron donor pair and a proton and that kind of an attraction. So it will be between, say, water and alcohol. It would be even be between benzene and water in a particular direction though, because the pi electrons in benzene can get attracted towards the proton of water. So only in that axial direction. So it will have a lot of different kinds of manifestations. Fine. So this is the second kind of an interaction, and it has got fairly high value. So you can roughly estimate it. 1 kilogram of water has enthalpy of vaporization which is 2260 kilojoules per kg. 1 kg is approximately 55 molar, 55.5. So if you divide the two, and then each molecule will have 2 bonds. So if you divide that by 55 into 2, you will get approximately 21 kilojoules per Avogadro number of hydrogen bonds. So that is the normal range around which you will find these values between proton and oxygen. So it is intuitively you would be able to roughly estimate what is going to be the value if you know what is the latent heat of vaporization. Okay. Then water also is a permanent dipole. Okay. So it is 1.85 dBi, which is the stat coulomb centimeter into 1 minus 10 raised to minus 18. Okay. And which leads to the dielectric constant of water. You are familiar with dielectric constant of water. Okay. 72 is the value. Fine. It is because of this permanent dipole which is there. So these three are considered by Hildebrand as the major sources of enthalpic contribution, and he conducted this he conducted several studies to identify the Hildebrand solubility parameter, the contributions in 3 dimensions. So the third dimension is the dispersive energy which comes out of this, you know. So these only 2 dimensions are shown here because the dispersive energy does not contribute as much as the hydrogen bonding and the dipole-dipole interaction. So water, you can see, exhibits both hydrogen bonding as well as dipole-dipole. You have something like ethylene carbonate, which is more on this axis, which is the dipole-dipole interaction. You have hexane, toluene, benzene, chloroform here. They are merely dispersive interactions. Fine. So all the molecules here behave differently with respect to each other and with themselves. So you can see that the molecules which are closer to each other they tend to form ideal pairs. Molecules which are away from each other, they tend to form non-ideal pairs. Okay. So this diagram is also a very important diagram, which generally if you have the shape in mind, you can then make use of it for creative work. And then you can see that most of the, so toluene benzene, because they are very close here, you can see. Water methanol, so methanol and water also, they are close but not as close as toluene benzene. So therefore there is a slight distortion here, water methanol, whereas you can see this completely symmetrical. Fine. And likewise you have the entire phase separation between water and chloroform because chloroform is here, water is here. Right. So this diagram becomes very helpful to guess what is likely to the behavior. We also make use of the polar additions of various locations in this diagram for designing new solvent combinations. Consider, for example, you have a mixture of A and B and you want to separate them together from each other. What you do is select a solvent here on this axis, which is very much away on this axis, another solvent here which is away. Now these 2 solvents will not mix with each other. They will form 2 separate phases. And this solvent will preferably dissolve this. This solvent will preferably dissolve this. This is one of the very simplistic, arguments I am putting across to you. Okay. One has to, in fact, this has to be done with a vector diagram. For example, if you have A and B here like this, you don't have a solvent here. It is possible to make a mixture of S3 and S4 so that you have a mixture which is here and make use of that to extract out B. Okay. So in that sense, this is a very powerful kind of a treatment and reasonably simple also. It has approximations, but as a first guess for designing processes, etc., and understanding how the systems will behave, this is a very useful stuff. So we are going to solve a problem. Read the problem carefully. I will just explain to you. I mentioned to you about neem oil and the constituents of the neem oil as well as other bioactive molecules which are present in neem. Now there are several of them. One is azadirachtin, another is malintroiol. Most of them are antifidants. They are also anti-nematodes and they are insecticides as well. Fine. Especially azadirachtin, it is very powerful. So at one time azadirachtin was considered to be one of the important substitutes for pyrethroids for organic farming, and it is important to extract azadirachtin from neem at a low enough temperature. So one possibility is that you can do physical expelling. So you use a screw press, and in the screw press, you expel up that oil. Fine. Now that oil will contain some azadirachtin, and then you can separate the azadirachtin from there. But then again there is a problem. The problem is that when you want to separate azadirachtin from oil, you have to get rid of the oil, and that may require higher temperature. Fine. So therefore, what solvent can be used in order that azadirachtin can be removed from the oil and then recovered at low enough temperature is a problem. So this is one of the problems which has been stated here, and if you read it carefully, your task is to estimate the hydrogen bonding and polar Hansen parameters of azadirachtin, plot the values on a graph paper together with those on the solvents and triglyceride oil, indicate which are the best solvent systems and which are worst for the job, using concept data of Hansen solubility parameters, and the data is given on the next page. So these are the group contributions for estimation of Hansen solubility parameters for different groups. Okay. So for example, if you take CH3 group, now it is not contributing to hydrogen bonding or the dipole-dipole interaction, but it is contributing to volume, centimeter cube per mole. Fine. If you come to say this ether bond, then it is contributing to volume, it is contributing to the hydrogen bonding, it is contributing to even dipole-dipole. And then the contribution because of the dipole-dipole interaction is given by sum of these divided by the total volume, and sum of these divided by the total volume. These are the known Hansen solubility parameters for some solvents, as well as the triglyceride oil I have estimated and put here. Okay. So you have to only estimate the hydrogen, the values for azadirachtin, and what you should do is mark the various groups on azadirachtin first, and then you would be able to fill up that table. Acha. What numbers you have already estimated? How many groups are there?
This much.
You have to count the number of groups. Yes.
So for CH3 we are aggregating 1 line.
Yes.
So this is
No, there is nothing. It is just because this is on top of it. It's a stereoscope. No? So this is one single bond. Count the number of groups and put on that table. Then you will.
so I'm counting now.
काउंट किया आपने? अच्छा, ऑलरेडी. ओके, गुड. ग्रुप्स काउंट करो पहले, because then you would be able to mark the groups and count them. पहले ग्रुप्स मार्क करो, then count them. हो गया?
Just calculate the groups.
Yes. कितना आया?
Delta P is 7.76.
How much?
7.76 polar part.
And
The hydrogen bonding is 4.16.
no, कुछ mistake है, but that is all right. Yeah.
This is sorry.
Which one?
This one.
This one is only one C with one bond. Huh? So this is C given here, number 2.
So is it C?
2 कहाँ है देखो. 2 is here also. It is just that it is shown stereoscopically. This is also 2.
Is
समझा
it
ना?
like, yes, is it like this?
CH2, हाँ, correct. Yes. Yeah. Show me. You are very close. 8.91 is delta H is 8.57, and this is 9.3 is 8.83. So somewhere small error somewhere.
We have to do like this, na? This multiplied by this and
Correct. Yes. आपका 9.39 आया. अच्छा. थोड़ा देखो. ग्रुप आइडेंटिफिकेशन में कुछ मिस्टेक हो सकता है. हो गया? क्या?
सिर्फ काउंट किया
हाँ ठीक है ना.
करेक्ट है ना इसके आगे
Let me see. CH3 5, I have got 7. CH2 4, correct. Either these are 3, you have got 4. Check कर लो आप, हाँ बाद में. Then here you have got, I have got 9, correct. Then this is 1 here somewhere. Then 7. This is 7.
दिस वन
Then this is 4, correct. This is 5, we have got 6. This is 3. Correct. I think you will have to understand how the steric representation of a molecule is also, it has to be used very often. So the symbolism used for showing a steric orientation of the molecule, you must be familiar with. So I see wherever there is a very planar kind of a part of the molecule, everybody is right. But wherever there is a steric representation given, that is the bond is projecting out of the plane or going inside the plane, then people have made some mistakes. Okay. For example, this is nothing but CH2, okay, which is coupled with this oxygen as well as this. This is also same. So both are given the number 2. Although pictorially they appear different. This is also a similar case. Here this bond is coming out of the plane, but it is essentially CH2. What I will do is, I will show you the rough answers. Okay, you can see this is how the groups have been counted. Their total volume is counted, and generally this volume is estimated from the density at the boiling point for a given concentration. Okay, so it is very easy. Sometimes the volume is not given as a data, but we can make use of the simple density of the liquid and get volume. These values are given, so these sums are given, and then this is the answer which I have got. There may be an error, I am not very sure, but most likely there is not likely to be an error because nearly 10 classes have verified this number. Fine. So once you have this value, okay, the next step is that you plot on the Hansen diagram. So the azadirachtin is shown here, the triglyceride oil is shown here. Everything is not shown here, okay, so only the relevant solvents are shown. Now supposing you want to remove the triglyceride oil, or rather the azadirachtin from the triglyceride oil, what will be your choice of the solvents? Any guesses? Which one? Ethanolamine? Well, one has to also take into consideration ethanolamine is a very reactive compound. Okay, so when you are looking at something which is extremely delicate molecule, one would not like to use ethanolamine, but which is the nearest other solvent, and also that solvent must have a very low boiling point, and I can see methanol is one of those. Fine. You can also use diethyl ether or carbon tetrachloride to retain triglyceride oil in that layer. Okay, so that is another possibility, or you can use simply triglyceride oil and this combination. In case methanol and triglyceride oil during your practical experiments, they don't tend to phase separate very clearly, then it is better that you can use carbon tetrachloride and triglycerine, so that this and this will be definitely separating. So the triglyceride oil will go in carbon tetrachloride and the azadirachtin will go in methanol. So generally the vectorial distance is considered to be the key for choice of the solvent from the oil. Yes. Yes, it can be triglyceride only, but there is that is where I suggested another possibility, that supposing triglyceride also starts dissolving in methanol, then you may have a second solvent which does not mix with methanol, and therefore triglyceride will come there. So what will work we don't know. So there only thing is that out of say 100 different solvents, you are now shortlisting only a few on which you can focus your experimental work. Okay. Otherwise, if you want to do empirically, you open Perry's handbook, you can have hundreds and thousands of solvents, and if you want to do empirical work, then that will take such a long time. So this approach tells you that now how you would like to focus your experimental work on those likely candidates which will be successful. Okay. So this is I am uploading this so you can verify your answers. And one problem I am giving you for your homework, and whatever you are been given as a homework, I would suggest that you please solve those problems at home. If you have any problems, come back to me. Okay. So this is another interesting problem which is about packaging material. Okay. Limonene, last time I mentioned to you, it's one of the fragrance molecules which gives you that initial sharp note which actually contributes to freshness. So soaps like Liril have limonene. So now one would like to have limonene in soap, but we do not want limonene to vaporize and get lost on the shelf. So what is the material or the barrier film that we can use in order to retain limonene in soap? So this is the problem in packaging. Okay. Now generally the permeability of any molecule through a barrier film is proportional to its solubility in the barrier film. Fine. So we can use that clue and find out limonene would have more solubility in which of these three. So they are shown as polymeric with N-mers, but then all these groups, if you simply apply N there, they will get cancelled out. So you don't have any problem. And then you will find out which is going to be the most useful barrier film for retaining limonene in soap. Okay. So if you go into packaging development, this is a very, very simple approach to follow. Any question regarding this?
Polymeric.
Yes.
That N we need to just consider it as a single monomer.
No, you put N there, N will get cancelled. Yes. So this is a real life problem. These are the problems which are generally solved using these methodologies. So if you have any questions, we have another 4 minutes left regarding this problem as well as the previous problem. For the previous problem though, this is a very planar molecule, but I would suggest you start looking at the steric representation of molecules, especially if you are looking at bioactives. Their most activity contributions are because of their steric orientations. So those enantiomers are very important. So you must understand the symbolism for showing those kind of molecules. Yes.
Sir, what is significance of negative values here?
Do you get negative values?
Volume negative.
Oh yes, they shrink. Yes. They reduce the volume. Yes. So there is a 2 or 3 databases available for a large number of groups. I should have actually written down the source of these values. So next time I will upload it on the Moodle. So you would be able to refer to these values from the source books. Yes.
What is the instrumentation that we use to measure these values?
Generally what is done is that these contributions are extracted from the actual experiments carried out on, say, a larger group of molecules, and it's it's a principal component analysis which is done for every single component, okay, for a large number of different molecules and from their properties. And validation of these values is a very tedious kind of a job. Like UNIFAC also, it is the same thing. So you have activity coefficients known and interaction parameters known, which are measured actually from, say, vapor pressure data. And then you would start playing with what is likely to be the contribution by individual groups. And when you regress that entire data, you will get the contributions made by individual groups. Now, generally, those contributions are valid for normal compounds, but sometimes there will be deviations. So, the contributions which are given in the group contribution method are average contributions. In actual specific cases, they may vary. So, essentially, the activity coefficients are found out from empirical data, and from that empirical data, you form a model that this group, etc., its contribution is this, etc., and then you extract that. So that extraction of data is a huge work. But your question is important. that it is not based on a priori prediction. It is based on actual empirical data on activity coefficients from which these values are extracted as they are available to you. There will be methods for ab initio predictions as well, but they will also get validated only comparing with empirical findings.
For that particular compound,
Yes, limonene.
for learning, that data may not be available. Data means, as you say, like
Yes, so only for, when the data is not available, then the group contributions really come to your help.
why most of the means many times why this data deviates from the experimental values.
Which data you are saying? The one which is predicted by this? The reason is that all correlations have a certain error band around it. Okay, so you are making use of only the average values, but the entire deviation is not accounted for here. So therefore you are making use of some average values in order to make the prediction for an unknown molecule.
So for even in Aspen, we use group contribution method for the calculation
Yes.
prediction of isotopes and other non.
Yeah, but there you will use lots of contributions. No, you will use NRTL, you will use UNIFAC, all of them are group contribution methods. Yeah.
But in that case, many times it will not predict the right.
No, what happens is generally activity coefficients for liquid-liquid separations and activity coefficient for vapor-liquid separations, okay, the two do not match always, and therefore Aspen will also give you group contributions based on liquid-liquid separations, okay, and vapor-liquid separations. So you will have to be careful about which data set you are using or which groups you are using. So Aspen will give that. There is also a situation, for example, very often when you use Aspen, okay, if you make use of NRTL or say UNIFAC and you get phase separation, designing a distillation column is very difficult. Fine. So what you do is you approximate that vapor liquid equilibrium using Wilson. So these are small little tricks which people use so that the convergence becomes easy. ठीक है? Okay, so I will upload this on Moodle. Huh? And shall we have the test on next Tuesday? Huh? We will? Okay, ठीक है. Huh? So whatever we have covered so far, but then I think you must do your homework, all the problems which you have solved in the class and given you as homework you must solve. ठीक है? Okay.